So today we're going to talk about graphs. What are graphs? Great question. No one likes these. They're confusing and awful.
Mm.
They're relations that are non-linear. Or, well, they're linear. They're just extra special.
All over the
So,
place.
yeah. So first we had our linked lists. Nice little straight lines, right?
Hmm.
One direction, two direction. Essentially, since we're all talking about databases today, a one-to-one relationship. And then we had our binary search trees, or little binary trees.
One to
A
many.
a one to two relationship. Yeah, a one to many relationship, but mostly just two. Got left and right. A one to many relationship. And now we have graphs, which is a one to many, which is basically many to many. They're interconnected. So before, when you were asking like, hey, what about this linked list? Does it go in a circle? No, because that's a graph.
Yeah.
So these are some great examples that are actually in the README of things that are graphs. So we have all kinds of weird and wonderful ways of having relations. These are related in very many different ways, and that is why they are complicated and awful. So today we are just going to build the graph. I believe it's in graph intro.
Well, I
Yeah,
mean, graphs. Is it?
objectives, other
What's it?
objectives, graph
Oh,
intro.
okay.
Go ahead and drop it down. Oh, nope. Here, is it? It is not in graph intro. Never
Well, these
mind.
images.
Let me open up mine and find out where this little file's at. It is in projects graph.
Oh,
And
okay.
now
So I was going towards the right one.
you were and I was wrong. Okay. So graphs are collections of related data. They're like trees, except the connection can be made from any node to any other node, even forming a loop. The nodes in a graph are called vertexes or vertices or verts, and the connection between the verts are called edges. So let's just go over that again. This before was called a,
Node.
and now it's called a,
Vertices.
right, a vertex.
Or
Vertices is a plural
vert.
of a vertex for
Yeah.
all of those language nerds out there, like me. So, and these things between the vertices are called
Pointers.
edges.
Edges. Okay.
So these things are called the edges, and so the arrows are the edges, and the nodes, quote, quote, are the vertices. And these are different because,
They go all over the place.
right, they go everywhere, and it's kind of like not as organized as some other things could be. So we've got graphs everywhere. They can form loops, they can form stuff, and this is how we do a lot of things. It's a little confusing sometimes.
It's
This
almost
is,
like a neural network.
yes, it is pretty much exactly like a neural network. Kind of like. Graphs can represent any kind of multi-way relational data. This could be a collection of cities and linking roads. It could be a collection of computers on a network. It could be a population of people who know each other and Kevin Bacon. It could represent trade relationships between nations and so on. There are lots of different types of graphs. There's different ways to represent them with their adjacency matrix, the graph, and the adjacency list, which you can find in the README in some stuff in the, I don't know where which README this one is.
Is it in
So
this?
let me see. Did Graph Intro have a README? Yeah, open that up. Yep, cool. I'll change my annotate, turn that off, and we'll get to, and keep scrolling down. Scroll, scroll, scroll. So here we have our definitions. Scroll a little bit more. I'm just going to read directly from this so I sound smart. If the edges are one way, so one way is essentially our dot next, they only go in one direction, the graph is said to be a directed graph.
Okay.
If there are no arrows, the edges are bidirectional and the graph is an undirected graph. If there are no arrows, it goes both ways. All just directionless and wandering like me in my 20s.
I think most of us in our 20s.
So this one up here is
That's the directed.
Yeah, they go essentially in one direction. We just kind of, I guess we have to assume the direction. And then a little lower, we have the undirected. An undirected graph, which could represent as a social network like Facebook. Alice is friends with Bob, Carol and Dave. Bob is friends with Alice and Dave. Carol is only friends with Alice, and Dave is friends with only Alice and Bob. This is where everyone stops listening. So, Alice is friends with Bob, which means that Bob is friends with Alice. Alice is friends with Carol, friends with Alice. And Dave, also friends with Alice. Bob is friends with Alice and Dave, but not friends with Carol. And Carol is only friends with Alice. So, as we see, we have this very confusing, poorly drawn graph over here, but it is essentially this one. See?
Yeah.
In the above directed graph, we can follow Alice to Bob and Bob to Alice, Carol to Alice and Alice to Carol, and Dave to Alice and Dave to Bob. Poor Carol, only one friend. All right, continue the scroll. So we have cyclic and acyclic graphs. So if a cycle can be formed, as in you can follow the edges, and the edges are
Pointers.
Yes, our arrows. If you can follow the edges and arrive again at the beginning, then the graph is cyclic. So this graph is
cyclic. So, in other words, if they all connect.
If they all connect in a way that brings them back together again. So this graph is acyclic because over here.
Yeah, there's no connection there.
Right, even though that this part of the graph's got a little cycle there. There's no, so then we have dense and sparse. A barf. Wow. I'm not even drinking my beer yet. A graph where most vertices are connected to each other is considered dense. A graph with less connections is sparse. There's no exact cutoff for the specification, though you could say a flight map is more dense than a subway map. This is true. All right.
Well, yeah, because a flight map goes in a straight line, a subway map is not going to go in a straight line, right?
Well, also a flight map has got, so when you look at a flight map, so let's just draw a quick little like United States here. That's Chicago, that's New York, here's Miami, and then over here somewhere is Mexico. So when you have all of these hubs, Miami flies like everywhere. You got to go to Miami to get to like all these places. So it's going to have all of these little vertices here, right?
Yeah.
There's a million things. And let's not even get started with New York. You got like, you're going all the way over here. This is Europe. You're going up here. That's Canada. That's some other parts of Canada. You're going to go to Chicago over here. So there's so many of these like interconnected things, right? Here's a tiny airport that no one goes to. Here's another tiny airport that no one's ever heard of. So you have all of these just crazy, crazy lines and locations of going places. That would be super, super dense. But a subway system, yeah. So this is the subway system near where I lived in Berlin. This was the U2, went here. And this was the U7, went this way. And right here was the U4. That's really not that dense.
Yeah, because you don't have as many connections or
yes. Vertices.
Yeah, vertices.
So this is not as dense. A flight map is very dense. Does that make sense?
Yeah.
All right. Graphs with values known as
weighted graphs.
Yes.
Weights.
So the value is now the weight. So before a node had a value, a vertex has a
weight.
Good. Associated with the edges are called weighted graphs. The weight is dependent upon the type of graph. A graph of road network segments might have a weight represent the length of the road. The higher total of the weight of a route on the graph, the longer the trip is. The weights can be used to help decide if a particular route should be chosen over another. Oh, that's really cool. So we have this little route here. This has a different weight than all of these points. I wonder what... And there's heavy traffic. Traffic probably has some crazy weight to it. All right. Weights can be further modified. I mean, again, when we're talking about weights, we're talking about the
weighted graphs. Or you're talking about the vertices.
Talking about a value. The value. So in our brains, we can say values and weights are kind of like each other. Take a drink. Weights can be further modified. Scrolling on down. If one were to build a bicycle, roads with bad car traffic or very steep uphills could be getting unnaturally large weights, so a routine algorithm would be unlikely to take them. And this is how Google Maps avoids freeways when you ask for walking directions. Oh, that is so cool.
Or like if you ask for no toll roads when you're driving.
Yep. So now we have directed acyclic graphs. Let's make a guess. What do we think that means?
It's an acyclic graph that's directed.
And what does directed mean?
Can I scroll back up?
Nope.
Okay, the directed is when they all meet back up, right?
Yes. Directed is when it's got arrows. Acyclic means...
Or wait a minute. Acyclic is when they don't all connect.
Right. Acyclic. A means A in whatever language this comes from does not cycle. Acyclic. No cycling.
Hey.
Aha. Directed, meaning it got the arrows.
Yeah. Okay.
Dags can model many different kinds of information. A spreadsheet can be modeled as a DAG with a vertex for each cell and an edge for whenever the formula on one cell uses a value from another. Value from another could be called a
Wait.
yeah. A topological ordering of this DAG can be used to update the cell values when the spreadsheet is changed. Similarly, topological orderings of the DAGs can be used to order the compilation operations in a make file. Don't know what that means. The program evaluation and review techniques uses DAGs to model the milestones and activities of large human projects and schedule these projects to use as little total time as possible. That sounds like data science.
Mm-hmm. Sounds like neural networks to me.
All right, good. You'll be great at this. Combinational logic blocks in electronic circuit design and the operations of data flow and programming languages involve acyclic networks of processing elements. DAGs can also represent collections of events and their influence on each other, either a probabilistic structure, such as a Bayesian network, or as a record of historical data such as family trees or the version histories of distributed revision control systems. You know, they went from one type of real nerd to another type of super nerd. DAGs can also be used as a compact representation of sequential data, such as directed acyclic word graph representation of a collection of strings, or the binary decision diagram representation of sequences of binary choices. So this is pure data science and why all of us cry.
Data science ain't all that bad.
Sing this song with me.
Hey, we wouldn't have AI without data science.
Can't spell Ava without A, but we are bad at math. It is notable that Git uses a DAG to represent commits. A commit can have a child or more than one child commit in the case of a branch. A child can come from one parent commit or from two in the case of a merge. But there is no way to go back and form a loop in the Git commit hierarchy. Cool. So, do we feel educated now?
Yeah, my brain is swollen.
It swells with pride. So, we are going to go, and all we're going to do is go to our graph.py. Right here. Yeah, all set up. So
I think I might have started working on this morning on Friday.
yes, it's very probable. So we're going to import stack and queue. So Joanne, what is a stack?
A stack is like a stack of pancakes.
Right.
It's, what is it?
First
Last in, first out.
First in, last out. Yep, we're last in, first out. It's the same. Doc says that says is different, but I think that those words mean the same thing.
Yeah, basically.
Is the last one that goes out, and the last one that goes in is the first one that goes out.
And
It's
then
the
a
same
queue
thing.
is first out.
Yep. So we're going to import our stacks and our queues. So represent a graph as a dictionary of vertices mapping labels to edges. Cool. And so we brought in self. We have, where did my graph go? My graph went here. Yes, self dot vertices equals and
or a
wonderful an empty dictionary, because we're going to map one thing to another thing.
Okay.
So the first thing that we do is we set our dictionary, because we're going to have a label and our edge. All right, the next thing we're going to do is we are going to add a vertex to the graph. So what do we have here? Okay, we're gonna...
Well, it says if vertex ID is self.vertices, then you're just returning. So, in other words, if it's null, right?
Well, no, in this case is if... I'm actually really curious Because you're supposed to be able to have a vertex be multiple things. Oh, actually, because you're using a set, it automatically doesn't worry about that, right? Because
Okay.
sets are unique.
So then, in other words, if you pass in a vertex ID and it's already in the vertices, then it's just going to return.
Yep.
So you're not going to be adding anything. So the self dot vertices vertex or vertex ID equals set. So that'll be the actual where it adds.
And again, because it is a set, sets are unique. Have you used sets doing any kind of algorithms before or in Python?
Yeah, and if I remember correctly, isn't set kind of like its own type of dictionary, kind of like a dictionary?
Yes. And
Okay.
it basically makes sure things are unique. So if you are, it's a way of if you're like, hey, I need to make sure all of this stuff is unique and you don't want to do if thing in list, which is putting a for loop inside of a for loop, you can just do a set.
Okay.
And the set will go, oh, hey, no, this is already here, ignore you.
Okay,
So
now what's the time complexity on a set then? Is it the same as a for loop?
it's the same as a dictionary, basically. Because it just checks, is this here? As opposed to for thing in list, it cycles through the list.
Yeah.
If you say if thing is in list, it cycles through. It's a for loop and a for loop, and that's your time complexity. But a set is faster somehow. I'm not really sure. I don't know what the code underneath this looks like, but this is faster, and this is a way to like speed things up. And when you're working with graphs, sets are a thing that you definitely want to make sure that you use.
Okay.
So you can have this here if it makes you happy, but because you're using sets and because of the nature of sets and sets don't let you add duplicates, not technically needed.
Okay.
All right. So then we're going to add an edge. And Doc was super nice and gave me her code because she knows that I had a tough time with she knows I had a tough time with graphs my first time through. So, thank you, Doc. Add an edge. We're going to add a directed edge to the graph. What does directed edge mean?
Directed has arrows.
Right. So we are being passed in self, v1, and v2. So if v1 in self vertices and v2 in self dot vertices. So now we're looking at our set of vertices and saying, yo, are these two things here? Yes or no?
And if they are,
Then
it's
we're
saying, so if they are, it's saying to add then at that point?
if they are, so we're going to, now we have our set here, right? So we're saying self vertices at v1 right here, right?
Mm-hmm.
So at the key of v1, we're going to add the value of v2.
Oh, okay.
So this is a unique key value pair.
Okay, I see.
So you could have eventually like v3 and v whatever else, right?
adding them all into the same vertice?
Yes, because remember our pointers point to whatever we tell them to. These are crazy directed lists. So we're saying self vertices v1, that is our key. And then we're going to add the value of v2. And then this is raise, which is basically like catch for those of us who came from JavaScript with the then catch. Raise index error. It doesn't exist.
Just basically prints it for you, saying that it doesn't exist.
Yes. There are a bunch of ways to like raise flags and stuff. So this is this is your kind of like a print statement, but it's programmed in there instead of a debug left in there by the programmer.
Yeah, well, most of your methods, they have a raise error statement involved in there.
Yes. All right. Now we have get neighbors. So first we have our vertices or vertexes. So logically, our neighbors are
wherever the edge is pointing to.
Yes, whoever those edges are pointed at. So these are the neighbors.
Which could be multiples.
Yes, which could be multiple. So before, when we had set up this v1 and I was like, yo, so we're making if the key's here and it's a v1, so we got our key. So it's basically going to print the values.
Yeah.
So return all the neighbors of a vertex.
So in other words, this right here where we're adding an edge, this is not, well, so to me, it's more like, okay, we're saying connect these two together is what it's saying.
Okay. So now we're going to scroll up.
Sorry.
So we're going to get the neighbors. I gotta talk these through to myself too. So we're going to get all the neighbors of a vertex, return self.vertices vertex ID. So what are we returning?
We're returning the vertices, the vertex ID.
We're returning the whole set where the vertex ID matches. So you would be printing this whole set here.
Okay.
So this is your house, and this is all the people on your block that you may or may not like. All right.
You gotta add trees in there. I got lots of trees.
All right. Well, we like the trees. I was talking about the people. All right. So we have a BFT. Do you remember what that means?
Breath first search.
T stands for search?
Breath first transversal or transverse, right?
Traversal.
That's it.
Breadth first traversal. All right. So
say that fast.
Breadth first traversal. So it looks like this is where y'all started and then exploded. So
well, we started out with the pseudo first of how we need to do it.
Okie dokie. Let's get all the way down. Get all the way down. All the way down. All right. Excellent.
So we started out with this, and then somebody came up with a better idea.
That looks like Doc's code. So
I don't remember.
So the first thing we do is we initialize a queue. And this is just like when we were doing our other traversals and we created a queue for our breadth first traversal. So our queue goes from where to where?
First in, first out.
Right. So we're going to be making a list of our nodes in order as much as possible from the bottom to the top. So first we make a queue, and a queue is kind of like a list. The next thing that we're going to do is in queue. What does that mean?
To start.
Means we're going to start putting stuff in there. We are going to put stuff in our queue. Right? So we're going to put all of our... Now, what are we putting in the queue? The weights, the values, the nodes, the vertexes. What are we putting in there?
Well, being that we're talking about graphs, so it would be the vertices that you're putting in there, right?
Yes, it will be the starting vertex. All right, and then the next thing we're going to have is a list.
That's passed in up here, right?
Yes.
Yeah. Okay.
That's been passed in. And the next thing we're going to have is a list of places we have visited. And this is a set. And what do we do? And what is really cool about sets, Joanne?
They're kind of like dictionaries and they're unique.
Yes, they're like unique little dictionaries. So if you've already been to a vertex, can you go there again?
Depends on which one.
Look at this. Look at this. Look at the set.
Okay. No.
No, that's right. So, like, if America is a map of 50 vertexes, and you've already been to West Virginia, are you going to go back?
No, I don't want to go back to West Virginia.
Exactly. That's why we use a set. All right. So now in our queue, we have a size. Remember how we had that previously. And our size keeps track of
the length of the
how
graph.
many things are in the queue.
Oh, okay.
So first, we're going to add stuff to the queue. Then we're going to take stuff from it. So as long as the size of the queue is bigger than 0, so as long as there's stuff in the queue,
then we can take stuff out.
Right, then we can dequeue. My favorite place to go get ice cream. So V for something we've recently visited is going to be q.dequeue. So whatever is in the front of this list, we're going to pop out, essentially.
And put it somewhere else.
Pop it out. Boop. And we're going to put it, or we're going to try and put it, in the set.
So that way then you're not going and revisiting the same thing over and over again.
Yep. So if V is not in our visited queue, we're going to add it to our visited queue, or to our visited set. Pop, pop, pop.
Is there a reason why we're printing first?
So we can see it. I think the directions are probably to like print the thing.
Oh, okay.
So in this case, it would be to print, since we're probably having to print the vertexes in order. Then for the next vert, as we define it there, in self.getNeighbors vertex, which this is our friend. What is this called?
What? The V? Oh, the get neighbors. That's everybody around it.
Which is our favorite friend, recursion.
Oh, yeah, recursion.
Recursion. So we are recursing our function. We're passing in our next vertex. And for every next vertex in self.getNeighbors, so for our next vertex in self.getNeighbors, pass in the V, and we're going to add this to the queue. So again, recursion is where things kind of gets hairy, right? So we're going to call getNeighbors on our vertex. So we got our vertex going, and that's doing getNeighbors. But we're also in queuing the next vertex. Boop.
Yep, you're putting it in The visited.
So this is going to continue going on our visited object, on our little vertex object here, while the next vertex is being searched. That give you a headache?
No, not really.
Awesome. So we've got one recursive function going, and also inside of a while loop, which is probably has another while loop inside of this, and everything goes on forever until we reach our final destination.
It's just reminding me of neural networks because in neural networks, it does the same thing depending on which one you use. You would have recursion to where it goes to the hidden layer and then it takes that hidden layer and puts it back to the input layer, and then the input layer runs through the hidden layer again, and it keeps doing that to retrain it until it gets the prediction correct.
You definitely just said a bunch of words that I will nod with.
Well, just all you have to do is ask your husband about it.
He has definitely said those kinds of words to me before.
And you just glaze over, right?
Oh, every time. We just trade and I start talking to him about databases. All right, so now we have the depth first search. Or the depth first, what's the T stand for?
What was it? Traversal.
There you go. And you got a sound effect when you got it right. Boop boop.
Even though I put it on silent.
So okay. First we went to see how wide it was. Now we're going to see how
deep it goes.
Yeah. All right. So we have surpassed where Josh went, it appears. All right. So the last time we used a queue. So this time we're going to use a
stack.
Yes. So go ahead and instantiate a stack for me.
It's capital S, right?
Yep. Is this a class? Awesome.
Then,
S equals stack. And so the first thing we're going to do is we're going to add something to the end of the stack.
Okay, so we're doing a pen.
Sorry, to the beginning of the stack.
Okay.
We're going to push.
Push.
Yep.
Whoops.
S dot push. And what are we going to pass in there?
The vertex.
Which vertex?
The starting vertex.
Very good. All right, so we're going to pass in our starting vertex.
Why is it not giving me any hints here?
So then, just like the last time, we're going to have a
if.
No, we need something before we have an if. We got a stack, now we need a, don't look, it's places we've been.
Oh, visited.
Right, which is a
list? No.
It's kind of like a dictionary.
Set.
Very good. All right, so we're gonna have this is gonna be pretty bog standard. So while the size of our stack is greater than 0, V equals
that would be visited, right?
So this is just something that we're looking for. So if we push to put something in the stack, what will we do to pop something out?
Remove.
S dot.
Just do pop?
Yep. So S dot pops. This is whatever's been added, and we're just gonna pop it off.
Okay.
First in, first out. So put it in, pop, pop. First in, last in for whatever it is. It goes this way. Alrighty. I keep open the wrong notes. Still the wrong notes. Here's the good notes. So if V not in
visited,
then we're
right?
gonna then we're going just like last time, we're gonna print the V. Then we're going to add it to our set.
Oops. And then it would be, so it would be V, or no, it would be visited, right?
Visited dot
Then,
dot add, because it's a set.
oh, okay. And then it would be V, right?
Yep. And then we're going to do just like last time. For next vert in
Oh, my fingers don't want to type. For next vert.
in recurse.
In self, get neighbors, right?
Yep. Oh, sorry, this is not recurse. This is a separate method for self.get neighbors. Bad even. Then
We're gonna do. We're not doing an in queue, so we're gonna have to do.
oh, is the opposite of a pop.
Okay, so it would be push.
Right.
So V dot push though, right? Or is it
S dot put S
S
dot
dot
push.
push and V
Next vert.
next vert?
So we're just making a big old thing that is continuing on forever.
And how do you end the while loop?
The while loop is exited when you reach 0. So when there's nothing left in your stack, you are done.
Okay.
So that's our first thing. While s dot size is greater than 0. So as soon as it hits 0, that's your exit strategy. All right. Is that fun?
Oh boy.
Yeah.
More toys.
All right. So now we got even more fun. There's more fun yet to be had. Why, yes, indeed.
Recursion.
Recursion. Yes. So, and please ask as many questions as you feel like, because the more I explain it, the more it makes sense to me.
Okay.
So now we have a depth first traversal recursive function. So our exit strategy goes first. So first thing we're going to do is we're going to add a parameter here.
Okay.
So what sort of thing have we been adding every single time?
The visited.
Right. So let's pass in visited. And what is a good default value?
1. I don't know. 0.
Oh, sorry. I did it bad. So never mind. We don't have to do that. Starting vertex. So we're going to start with if visited is none.
Okay, so we're leaving visited as a parameter though.
We're taking visited out. Just delete that section. Make me look smarter. Alrighty.
Okay, cut.
All right.
Okay, so if
Visited is none.
it helps if I can spell, is none.
So then we're going to create a visited, which is always going to be a
Set.
woo.
Okay, did I spell something wrong? It doesn't like visited.
I don't know.
Not giving me anything.
Set equals set. Yeah, that's fine.
Well, yeah, because we haven't done anything with it yet.
Yep. Yeah, sometimes Pepe gets a little too excited. So then we're going to say visited.add. And what could we possibly add?
The self or starting vertex.
Woo! So first we're going to add it. And then we're going to print it. So visited.add starting vertex, print starting vertex.
I told you I'm a slow typer.
It is all good, So for child vert in self.vertices starting vertex.
Did I spell that right? Yeah.
Yep.
Okay.
And then we're going to access our starting vertex via bracket notation. Because self.vertices is not a method, it's a location, so we need brackets.
Oh, okay.
Yep. We're going to access it. So it's saying, hey, for all of these things, for all the values in our key, right? Val,
Okay.
val. So for child vert and self.vertices starting vertex, if...
So then a child vertex is just the value inside?
is the value, right? It's not the weight, it is the value and the key value pair.
Which the value can also be another dictionary.
It's going to be it's going to be a key, right? So this value is actually the key in another thing.
Okay.
So that's going to help us find if that's a key to more values.
Yeah, because it just keeps pointing to other sets then.
Right, so let's draw this out because I have a feeling this is going to be helpful to somebody. So we have our key, or let's call this K1. And then we have a bunch of different values. V1, V2, let's just do 2. So we're going to check. So we roll through and we've got our main vertex, right? This is our starting vertex.
Yeah.
So we're adding that to our visited. So then we're going to go for all of our children. So all of these for V1 and V2. So we're grabbing V1. So the starting vertex child, that's the first one, is V1. And then our next child is going to be V2. So we're going to do this twice, right?
Yeah.
Then if child vert not in visited, colon.
All right, Joanne.
Then we're going to recurse self.depth first recursive child vert visited.
Okay, self dot depth first recursive what now?
Child vert. So we're going to pass in V1 and then we're going to pass in V2 on the next time. So it's going to boop, boop.
Okay.
And then we're going to pass in visited. So we're going to have one set of visited have K1, and then we're going to have another set of visited is going to have K2. So it's going to go.
Okay, so we pass that into the same parameter because that's not going to work.
Yeah, child vert, comma, visited. So we're passing in our set. Right? So if visited is none, we're going to create a list. Oh, take this back by 1. Take that visited back. There you go. That's an else. Boop. And then take that everything back by 1.
All of this down here?
Yep. All of it's going to go back by 1.
Okay, but so now, wait a minute. Because we only have the starting vertex.
And that now that's going to be the visit. Now that's going to be visited.
Okay, so child
So
vert acts as a self.
no, there's no self. So if we look at, I'll draw it again. So here's
Well,
our
I'm
first.
just trying to figure out, like, here in the parameters, if we're using the depth first transversal recursive, then it's only got the one parameter that's being passed in, and we're passing in two parameters here.
Childvert and visited. We're passing in two. I don't know why it doesn't have. Hang on, let me double check. Maybe I did need to set it to self and I just like blacked out. Yes, we did have to set visited equals none. Why? Don't
Okay, so
second guess
up here
yourself
in the
like that, Ava. Yep, go add that up there. How dare I? I second guessed myself and I was totally right. So
none zero, or does it matter?
set it to none. So the first time it goes through, it's none. That way, we will create a set.
Okay.
So let's draw this out because it always helps me to draw. So first we pass in our starting vertex, which is going to be K1. And then we're going to pass in a null value, none. So then we create our visited, which is now a empty set.
Yeah.
All right. Great key value set. Boop. So then we're going to create our starting vertex by putting the K here. And our K, so for the child vert and our self vertices starting vertex. So we're going to go and look up in our vertices up there and say, hey, how many children does K have? And we find out that K has like 2 kids. K has V1 and V2, right?
Yeah.
So if the child vertex is not visited, so if we haven't already been there, we're going to take our V2 and add it to our V1 and add it to our set. And then
And then you're going to go through all of V1 until there's no more left.
We're still not done, right? So we're adding that. That's V1. And then we're also doing V2. So we're gonna have two versions going there, right? Bloop,
Okay.
bloop. And then we passed in the set. So our set is our visited. Our visited is no longer none. We've got this KV1, V2. V1 is going to get looked at by the first version of our recursion, right?
Yeah.
And we're going to see if that exists and how many children V1 has. And then V2 is going to get passed in. Now, because of print is over here, V1 gets printed first, and then V2 gets printed second, because this is the call stack. And the call stack makes my brain hurt, so we're not going to talk too much about that. But we're going to have V2, and then we're going to look at all the kids in V2. And let's say V2's got another 2 kids. So with V1 has child 3 and child 4. V2 has child 5 and child 6. So we're going to go and we're going to look at 3, 4, 5, 6. But 3 is going to have 2 kids, and that's going to be 7 and 8. And 4 is going to have 9 and 10. Is this making sense?
Yeah. Yeah, so it's just going down the tree.
Yep. And that's how we are passing it and 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 passing it. And when we get to none, that's when we stop. So for every child, as soon as we get to a no child, does it go?
No, it goes back up to the last one.
So if our final child either has no children or points to a place we've already been,
Then
we
it'll
don't
stop.
then it'll stop. Does that make sense?
Yeah.
All right. Then we have our breadth.
Search.
Right. Whoo. So, difference between a search and a traversal is
That one I don't know.
okay. A search is we are actively looking for something.
Okay.
So we are searching for something. A traversal is we're just wandering. We're aimlessly going without a purpose.
You're just a sightseer.
Yep. So yeah. So a traversal is we are wandering aimlessly through the park. Because without not aimlessly, we're walking with direction through the park. A search is we are looking for a bear.
Okay.
Or candy if you are food motivated.
Searching
So,
for a geocache.
yeah, exactly. So that is our destination vertex. We are looking for something. We are starting at a place and we are looking for something. Whereas a traversal is we're just starting at a place.
But you still have to have your visited ones so that you don't return, right?
Yeah, exactly. So this is a breadth first search. Is this recursive in this moment?
Well, breath first isn't because you're going line by line. You're not going side by side, right?
Awesome. So we have a breadth first traversal. So the first thing we're going to make is it a stack or a queue?
For the breath first, you would do Q, right?
Yes.
Okay, so we go back to Q equals Q. I hate typing this out because I always mess it up. Is that spelled right?
Q-U-E-U-E?
Yeah.
I hate that word so much.
Me too. Just write a Q.
It's got like 5 more letters than it needs.
Uh,
Then we're going to
then we have to have our visited, right? Or we're
no, we
making.
gotta add stuff to the queue. So we
Oh,
use
so Q dot add or no wait,
Q
it's
dot
Q dot.
NQ. And
Another one that I hate writing.
what do we put in our and what do we NQ?
The starting vertex.
Woo!
And then now we do
Then
our visited, right?
yeah, now we have her visited. So this is gonna start getting a little familiar. So while exit strategy. Remember, queues have a size. So while
Well, Q is a Q dot size.
mhm,
Q dot size is greater than 0.
perfect. Then we're gonna have our. Then what are we gonna do to our visited?
We're
Or
going.
our yeah.
Well, the visited you're gonna add to it, right?
We're gonna q dot nq. Hang on. No, our q. We're gonna deq the q.
DQ the Q. Okay, so it's visited DQ or is it Q
It's
dot
q equals q dot dq. My brain.
Q dot DQ?
Yes, hang on just a second. Let me look at something here. Path equals q dot dq. So we're going to create this as a path. So this is a new thing. So
Okay.
we have my brains. So path equals q dot dq. So we're going to create a path, a way that we're traversing. So our q is the things in our line. The path is on our route. And this is really important because this is something that will pop up in your GCA, like it, because it did pop up in mine, and I was like, I don't know what to do here, and I just made a circle, and I got 30%.
So now you would end up, it would be visited.add path.
So now we're going to do v equals path bracket minus 1. So now we're going to go to the last thing in the path.
Bracket minus 1?
Mm-hmm.
Oh, okay. Yeah,
All right.
okay, you're indexing. Okay.
So for our in queue, we are going to add our starting vertex in a bracket for some reason. If Doc was here, she would explain me why. So on line 134, our starting vert goes in a bracket.
Okay.
So that we are, in fact, making it a list. No. Keep the method,
Okay.
but we're passing in the vertex as a list. All right, there we go. So v equals path 1, negative 1. All right. Do. Okay. If v not in visited.
In the while loop, right?
Yep.
Okay,
So we're still in the while loop.
And visited.
Next line. If v strictly equals destination vertex. Or, yeah, destination vertex. Return path. So we're checking to see if we found where we were trying to go, and then how did we get there?
Could it be the reason why it's, well, okay, I'm thinking maybe the reason why it's -1 is, could it be because of the fact that you're like looking at the next? So if
It's because we're looking at the last thing instead in the path, and we're continuing to add stuff to this array. That's why it's the last thing.
okay,
Brain, it goes away. Okay, then outside of the if, so
the last if, right?
yep, the most recent if. There you go. Yeah, where my little blue line is. Visited.add v. So if it's not in the visited, we're just going to add the vert to it.
Dot add.
And then for next vert in self.getNeighbors v. So now we're going to look around and get all of the values in our key value pair, right? So we have our vert, and then we're going to get all of our friends. And then for each one of our friends, we're going to add it. So we're going to new path equals list path.
List path.
List parentheses path. New path dot append next underscore vert q dot inq new path.
Okay, wait. Dot append new
next vert.
Next.
New path dot append next vert. Then the next line is q dot inq new path. No. It's a method that you pass in a thingy.
Oh okay, yeah.
There you go.
Yeah.
Okay, so what we've got here. So we create our queue. And we have our visited. So we've got our queue and we got our visited. So first we start with our starting vertex, that's in our queue, and we have our visited, that's also going to have. So we've got our K. So we've got our key value set. So first we have our queue. Our Q gets passed as a list now. So we've got this in a list, which is going to be accessed. This is our last item in the list, right? This is our current -1.
Okay.
We're going to check and see if we've already been there. We haven't been there yet, so we're going to add it to our visited set, right? Then for every, so our path is also the same thing as our path is also a list. Okay, comma. So then we're going to add everything into our path. So if it's in the
path
vertex,
is basically pretty much the same as what you visited.
it's what you've visited, but it's actually the what you visited in what order. So the set says, hey, don't visit me again. The path is, this is how we got there. So for example, we have the key value of, let's say we're on our third thing. So we can have our set is only going to have K in it one time.
Yeah.
And our K is only, K3 is only ever going to come after K2 in this particular order because it's already there. But in order to get to K3, what if we had actually just gone K1 and K1 pointed to K3? So that's the path.
Oh, okay.
The set is K1 had a child, K2, and K3. Because remember our call stack. So the path, we're going to have a path from K1 that goes to K2. And then we're going to have another path that goes from K1 to K3.
Okay. So that way then you know where you got to go back to once you hit that end.
You know where you've been to in this particular order. So let's say we have another one that's like K1 goes to K3, but K3 has 2 kids and K3 has K5 because K2 has K4. And that's the end. That's the end of K2, right? And then K5 and then K3 goes to K7. I can't draw anymore. K7. So this is our path. K1, K2, K4, K1, K3, K5, K1, K3, K7. So those are different paths. But the set has K1, 2, and 3 in it. Does that make sense?
Yeah, because I'm just trying to think back to the visualization of the breath first tree. And yeah, because it always goes down the left side and then goes back up once it hits an end to go to the right.
Right. So in this case, we've got like a whole bunch of arrows pointing in a bunch of different directions. And let's say like this one has like 4 coming off of it, right? So we have,
we're just going to search all of those first before going back to that one again.
Right. So this is our path goes, let me get another color. We went here and here and here. We go here and here and here. We go here to here and here.
Yeah.
We go here to here to here. We go here to here. So those are all the different paths. As opposed to the set, which would have just said, okay, this one, this one, this one, this one, this one, this one. It wouldn't keep track of how we got there.
Okay, I see.
All right, now let's look at the depth first search.
Does your brain hurt now?
Actually, that one made a lot of sense to me.
Okay.
So.
Okay, so for depth first, we're going to do a stack.
Yes. It's so nice that Doc gave me this nice implementation. So I don't have to like break my brain trying to figure stuff out.
And then we're going to push, right?
Mm-hmm. And because we're working with a search in paths, we're going to push it in we're going to add it with square brackets.
Oh, okay. So we're doing the square brackets inside the invoking.
Yes.
And then we're doing starting.
Yep. Starting
then,
vertex.
Okay, so
Then
now we do our visited.
Which is a
set.
Good. And then a stack also has, now we're going to have our while loop, and a stack also has a size. So our exit strategy is wonderful. So then we're going to have our path. How do we add things to a path with a stack?
We push with that one, right?
We already pushed, so we need to
add.
Pop.
Just not add, right? Oh, pop. Okay, so s dot pop.
Path equals s dot pop. And then we access the most recently added to the path, which would be, so our v equals
Path -1 again.
Yep. And then we check.
And then if v not in visited.
Good. And then again, if
v not in destination.
If v is our destination vertex. So if v double equals destination vertex.
Oh, okay.
Then we return the path. Else, so we just go back.
Okay, so just visited dot add again.
Except we're not. Yeah, we are adding. So visited dot add v, because this is a set, so we add.
And then we're gonna do the for next.
Yep.
Also.
Or same thing. Next vert in self dot get neighbors v.
And then new path.
Good. Equals list path.
New
and then
path. This one would be, we use append on this one, or we use push?
We use append because we're just adding to a list.
Okay. And then it'd be the next vert, right?
And then we popped, so now we're
gonna push now.
Yep, to s dot push, and we're adding our path to our stack. So s dot push,
path, right?
New path. That's right. And if it's not there, so all the way back out at our while, I forgot to do this one above because I'm a terrible person. What do we return if we don't find anything?
None.
Yep, return none. And the same thing at line 147 because I forgot to have us return none. Oops.
Okay. Did I put it right? Yeah, okay.
All right, and then our final is our depth first search recursive.
Recursion.
Plug. Recursion. Marsha. All right. So we're going to add two things to our parameters. Can we have a guess?
Visited. Right.
And our default value for visited is good. And our next thing that we might want to use
path.
Excellent. And our default value is?
Right?
Yep. And our path is going to have a default value of none. All right. So first things first, we check if.
So it'd be if visited equals none, or?
Yep, if visited is none, then what do we got to do?
If visited is none,
then we
we
have
have
to
add. We have to make visited, right?
Right. That's right.
Okay, so visited is going to equal set.
Mm-hmm.
And we're going to do starting.
Mm-mm.
No.
Nope.
Just set.
It's going to be an empty set. And then the next one is
your path.
No, that's right. So if. Whoop,
So
up,
we're
up, up, up,
if,
up.
okay, if.
Up. Go back.
Back one more.
Yep.
Now path.
If path.
If path. Okay. Would it be an else if or an elif or it's if?
Just an if. So if path is none, so we're going to check and then we're going to check.
So path would equal set also? Or no?
It's not a set, it's a
right?
list. It's an empty list. All right. So now we go back outside of our ifs. And now we can add to our visited.
Okay, so visited.
Dot. And what are we adding to it?
Starting vertex.
Woo!
And we got to do that in brackets, right?
Apparently not this time.
Okay.
I think it's the way we're doing. Okay, I see. This is how she's doing it. Okay. So then path equals path dot visited. Shoot, not path dot visited. Path equals path plus.
Oh, path plus visited.
And no, not path plus visited. I just looked at the word visited and said it because I'm tired.
Oh, I understand.
Path plus, and we're going to put our starting vertex in the bracket here. So whereas before we had initialized it as part of a list, this time we're not doing that until we get here, which should actually remove some needs for some things, if I'm correct. Yep. Okay, so if our starting vertex, what are we going to check for?
Is none?
Nope, it's our, if it is our,
Oops, spelled wrong. Hello, Joanne.
So if starting vertex is our destination vertex.
Okay.
So if we found it.
Yeah, we don't have to go no more.
And so we return the.
Return the starting vertex.
Path.
Or we return the destination. Doesn't matter.
We're returning the path.
Path. Oh, okay.
So we want to see how we got there. If you just like, if it's the destination vertex, we could just break that test by going return destination vertex. I found it.
Oh, yeah, true.
So we're trying to find the path of how do we get there.
Okay.
All right. Then we do the same for loop. For child vert in get neighbors starting vertex.
Okay, why didn't it do it? Get neighbors. Now it's going to make me type it out.
Yeah, you got to do self.get neighbors.
Oh, that's the. I'm tired too. And then we're doing starting vertex in here.
Mm-hmm. Right. So remember, each vertex we pass in is the starting vertex. So
that Z and that X is too close for me right now.
Same. If child vert not in
if child vert not in path
visited. So we're making sure we haven't been there first. We're just adding stuff to the paths willy-nilly. We just want to make sure we haven't already been there. Then new path equals self dot recursion depth first search recursive child vert target value child vert destination vertex visited and path.
Okay, so child vert destination, right?
Mm-hmm. Visited.
Yeah, I did that right. Okay.
And path.
Okay, so what's the arrow for?
What arrow?
Your red arrow.
You scrolled down, it was pointing at something else.
Oh, sorry.
So, if new path, return new path.
Oh, okay, just if new path.
Yep, return new path. And then all the way outside, we never found it. The bear doesn't exist. We return
none.
Woo! So,
Now walk me through.
alrighty. Oof. Let me pull up the right thing to look at. Okay. So the first thing we do is we're checking. If visited is none, we create a visited set. All right. It's empty. If
Yep.
path is none, we create an empty. Yeah, make a one over here. An empty list. It's going to be a little bit bigger than empty, but it's going to be an empty list. So we're going to add the vertex that we pass in, which again, for the purposes of any and all arguments, is going to be k. So our path is empty. Path plus our starting vertex in this case is going to be k. We start with k. Is our destination our starting vertex? No.
No.
So then we look at all of k's children. K's got so many kids. So for every child vert, so remember we have V1, V2, V3, V4, and we've never been there before, if they're not in visited, we are going to have a new path, and we're going to create a new path with our recursive function that's going to have our child, V1, and our destination, and we're going to pass all that in again. Visited has V1. Then our recursive function k is going to have v2, right? So we've got two parts of that call stack going. So we have k, and then we have v1, because that is our first set. And then our next, so it's our first, we have k, and then our next one, our child vert we're passing in is v2, right? So v1 and v2 get added to our set. Right? We do that up here. So we do that right there. Then we add to our path. So this path has got K1 and it's got V1. And then this path's got K1 and V2.
So then, in other words, the path, where we do path equals path plus starting vertex, that's saying, okay, well, we're going to start at the starting vertex, and then we're going to add the path that it took to get to
where we are currently. So this is the path to V4 is K V2 V4. The path to V7 is K1 V2 V3 V6 V7. So that's the path to get there. Can different paths arrive at the same vertex?
Yes, but the visited cannot.
There we go. Awesome. Do 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 do. Gold star. All right. So that is just the very beginning of this how we make graphs. Does that make sense?
Yeah, like I say, my brain keeps going back to neural networks.
So basically, yeah, this is all right, invisible person who is a web student and doesn't understand a neural network. Does that make sense?
The invisible person ain't speaking up.
All right, so we're just going to assume that everyone can follow this kind of logic. So we're adding, so K1, V1, and V2 get added to that set. Then so we add our starting vertex to our set. Our path is going to go, 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 go. And going to go to very interesting places. So, yeah, so that's how that's going to work for us. So our set would be something like K1. It's our V2 set is not going to have V2. It's going to have K1, V2, and then whatever things we've actually visited, child vert, and passed in, right?
Yeah.
So we have visited them. But if we get all the way down, right? So let's say that our path, we get down to a location. We may actually get back to V1 again because of how graphs work. Right?
Yeah.
That's all. Whew. Okay, I am really hungry and I'm about to beg my husband for some food.
So we can stop sharing.
We can stop sharing. This is the beginning of graphs. I will see you tomorrow for some more fun graphs time. Thank you for honestly, this keeps me accountable even if nobody else is showing up.